molecules arrange themselves in crystalline solids. As we have discussed previously, the general characteristics of a solid is that it is nearly incompressible, and the solid takes a fixed shape and volume as a result of how the atoms are arranged in the solid state. In particular, we're talking about a crystalline solid, so there must be a regular repeating pattern of units. And these atoms or molecules are locked into position and do not move around as they would in the liquid phase. However, there are some molecular vibrations that occur, and this is due to the average kinetic energy and the temperature that the solid is at. If we were to discuss the general characteristics of solids, we can break things into several categories. There are molecular solids in which the molecules have the intermolecular forces of attraction between one molecule and another that are somewhat weak, but certainly strong enough to lock the structures or the atoms and molecules into positions. And these shapes form a regular repeating pattern. There are also metallic solids in which the metal atoms have delocalized bonding, and the bonding is holding multiple atoms in contact with one another. Likewise, there's ionic solids in which the anions and cations form close packing structures, and these close packing structures are such that it maximizes the electrostatic interactions or the attractive forces of the oppositely charged ions. There are also then covalently bonded network solids, and these are polymeric structures that can be either one-dimensional, two-dimensional, or three-dimensional, and these involve a myriad of various shapes, and a good example of them are things like diamond and graphite. Shown here is the solid state structure of water, the ice structure, in which the molecular structures are held together in the solid phase due to the relatively strong hydrogen bonding interactions, which are the interactions of individual hydrogen atoms with lone pairs of neighboring molecules. As you can see, the molecular structure results in a more general structure in which there are hexagonal units that are then locked together to form the overall shapes that you observe on the macroscopic level. These intermolecular forces, while relatively strong for intermolecular forces, are relatively weak, and indeed water melts relatively easily as a result of adding some heat, and therefore some of the hydrogen bonding interactions are broken. There are other types of solids that are molecular solids, and good examples are things like carbon dioxide in dry ice, or the close packing structure of neon. Metals tend to form close packing structures in which there are arrangements of the atoms in such that they form layers. Shown here is one layer of iron atoms, and you can see that we have a series of triangles which then fit together to form hexagonal shapes. And it turns out then that these layers that have the hexagonal arrangements of the atoms can then begin to stack with one another to maximize the interactions of the various atoms and minimize the empty space. This then provides the ability of the electrons to be distributed over many atoms, and the so-called delocalized bonding that is known as metallic bonding. There are two basic types of structures that can be formed by close packing of spheres, and these are based upon how the layers are formed. Shown on the left here is a situation that was referred to as hexagonal close packing. In this case, the first layer, which is designated as the white spheres with the letter A, they pack together to form a layer that is forming the or the hexagonal shape that's shown in red. The second layer is shown by the black spheres that sit on top of the first layer. These are given the letter designation of B, and they sit down into the so-called divots of the first layer. Each of these atoms then forms a tetrahedral shape as a result of that. And the second layer also is a layer of atoms that forms a hexagonal shape. The third layer for this structure is such that the atoms in the third layer sit right directly above atoms in the first layer, so that we begin to repeat the letter designations of each of the layers so that it goes A, B, and so on and so forth. A second possibility is shown on the right here, where again you have the first layer with letter A. The second letter or layer is B, but then the atoms of the third layer do not sit directly above the first layer, but are above a hole in the first layer, and so this gives a third layer that is designated as C. This is the so-called cubic close pack structure, sometimes also referred to as a face-centered cubic structure. In this particular situation, then, the two possibilities are often observed for various metals. Ionic solids are fairly interesting in terms of how they maximize their charge interactions. Generally, in an ionic solid, the anions are relatively large, and when they fit together to form a particular structure, they also then have to incorporate the positively charged ions in the empty spaces created by the packing of the structure. And typically these interactions then between the positively charged cations and the negatively charged anions are interactions such that several ions interact with the oppositely charged ion. There are numerous type structures in which the atoms pack together as closely as possible, and quite often classic examples of this are things like the cesium chloride structure and that of zinc sulfide, and so on and so forth. In terms of the final type of crystalline solid, there are covalently bonded network solids in which the bonds between the atoms are covalent or polar covalent bonds, and the structures are polymeric, either in 1, 2, or 3 dimensions. As an example, we have the structure on the left, which is that of silica, which is SiO2. The structure results in silicon atoms being bonded to 4 oxygen atoms, forming a tetrahedral shape, which then is repeated in 3 dimensions. A second example of a network covalent structure is that of graphite. This is a 2-dimensional structure in which there are 6 membered rings of carbon atoms that extend in a planar structure, and these planar structures stack on top of one another and are loosely held together by intermolecular forces. Turns out that the element carbon has several different allotropic forms, graphite being just one of the network covalent structures that can be formed. Turns out that a addition of heat to graphite under pressure can also convert the carbon atoms into the diamond structure, which is a three-dimensional structure rather than just the two-dimensional structure of graphite. In diamond, the carbon atoms are covalently bonded to four other carbon atoms, forming tetrahedral arrangements, and this then is repeated in the X, Y, and Z directions. In addition to those two commonly observed forms, it turns out there are two other forms of graphite-related structures, such as the one shown here. The one on top is known as Buckminster fullerene. It's essentially a structure based upon taking the six-membered rings and wrapping them into a ball that in many ways looks an awful lot like a soccer ball. These sheets that are seen in graphite can also be turned into the tubes that you see on the bottom here, and these are of great interest for their physical and electrical properties, and are receiving a lot of attention by various researchers currently. This table summarizes the types of crystalline solids that are observed. Again, we have molecular crystalline solids that are held together by intermolecular forces. The units themselves are either individual atoms or molecules, and these are often observed in molecular species such as water or carbon dioxide. There are also metallic structures in which there is delocalized bonding, and this is where the nucleus of the atoms are surrounded by a sea of electrons that are easily moved around. The three-dimensional structures often observed are usually in the form of close packing structures, and some good examples are the structures of iron, copper, or silver. In addition to that, we have ionic solids. Ionic solids are comprised of cations and anions that then have repeating structures that maximize the interactions of positively charged cations and negatively charged anions. And these generally form close packing structures where the anions are relatively large and the cations fill the smaller holes. And then finally we have network covalent structures that are observed for things like diamond and graphite.